Hey everybody, welcome back. I'll give people a couple minutes to join in. As usual, I'll be monitoring the chat on YouTube, the live chat. So if you want to say hi there, you may. If you have questions or things you want me to address, you can leave them there. I also have the Discord up, so if you have questions there, please leave them in the live streams channel from this module where I sent the reminder this morning, and I will address any issues that come up. Give people a couple more minutes to join in. All right. Hopefully you can all hear me all right. So I hope this is going okay. I haven't really seen homework submissions yet. I assume you're still working on them. Please don't put them off too long because there's another big amount of stuff due this week. So make sure that you're working through these organic structures and learning this because it is probably the most difficult thing we've done so far, and I want to make sure you have the help and support you need if you're having trouble with it. This week, we're going to look at properties of these molecules, specifically a couple properties, their boiling points and their water solubility, and kind of how the molecules interact with one another. So I wanted to take you through this document a little bit. Like the ones we did last week, this is, or I guess not last week, 2 weeks ago, this is supposed to be a kind of a self-contained module that you can work through with only the information here, and you shouldn't have to look up other stuff. But in my experience, doing this semester after semester, it does require a little bit of context, and I think it'll be helpful if I just walk through it a little bit. So we're going to do that. Okay. So much like the other ones, the ones we've seen in the past, there is some just general data here without too much context. There is a little bit of information in the top here. Bond polarities are determined by the electronegativity difference between the bonded atoms. Recall that CH bonds are nonpolar, but CN and CO bonds are polar. So we're going to stop there and kind of talk about what that means. Another page here. All right. So what is this term? Electronegativity. Yeah, okay. Not always sure I spell that right, but I think I got it this time. Electronegativity is the tendency to attract shared electrons in a covalent bond. So last time we talked a little bit about this idea of a bond being two shared electrons between two atoms. Like let's look at an HCl bond. So when we draw this line, remember that what we really mean is that we have two shared electrons. So those atoms are sharing those electrons, and that's what's causing that them to stay together and to actually do this thing called a covalent bond. Electrons, plural. There you go. But when those atoms are different, often the sharing is not even. So like in HCl, for example, if we kind of model what the electrons where the electrons are, they're not evenly shared between the two atoms like this. They're actually pulled more over toward the chlorine. Kind of maybe exaggerate that. Let's exaggerate that even more. So let's imagine the electrons spend most of their time around the chlorine and are just a little bit around the hydrogen. So there's this lopsidedness between the two. And what that does, because electrons are negatively charged, that means that this side that has more electron density, where the electrons are being pulled, that means there's going to be a negative kind of area around this side of the bond and a positive area around this side of the bond. Let's mark that. So a structure like this might have kind of a negative side and a positive side. And anytime you have a separation where there's one side one way and one side the other way, that's often called polarity, and especially when it refers to positive and negative. So like a battery has a polarity, right? A positive side and negative side. There's magnetic polarities, that's called north and south. Like the Earth, right, has its north and south poles. So when we have that kind of a separation in a bond, that's called polarity. Separation of plus and minus. So that, oh, sorry, my head's in the way there. Separation of plus and minus. All right, so we can use this idea of electronegativity to figure out if bonds are polar. So if we had a bond that we didn't know if it was polar, like CO, and we wanted to know, is this a bond where the electrons are getting pulled more to one side or more to the other side? The way we figure that out is we look up the electronegativity. This is a quantity that you can look up on a table for each atom, and the links that I have in Blackboard to those book sections have all the electronegativities of the elements. So carbon's electronegativity is 2.5, and oxygen's electronegativity is 3.5. So what we want to do is calculate the difference for that particular bond. So the difference, that's a delta, means difference in a lot of different fields. So the difference in electronegativity is going to be the difference in these two. So that's 3.5 minus 2.5 equals 1.0. If that difference is greater than 0.4, then we call that polar. If it's less than 0.4, then we call it nonpolar. So here we have a difference of 1.0. So this bond is definitely polar. And so that's what's going on in this other, in this first section here, where it sort of assumes that you already knew that. CH bonds are nonpolar, but CN and CO bonds are polar. And that comes from that electronegativity. CH, the difference between C and H in electronegativity is about 0.4. So it's right on that nonpolar polar line, but it's considered nonpolar. And then CN and CO bonds are polar. Also, anytime you have the two elements bonded together, or two atoms bonded together that are the same, so like carbon and carbon, that has to be nonpolar because the electronegativities are exactly the same. So the difference is always 0. So any bond between two of the same elements is always nonpolar. All right. So now we know a little bit about that. Water, HO bonds in water are polar. And so therefore, when something is more polar, it will be more soluble in water. Another thing that I don't know if they define here. Oh yeah, so then it's defined right down here. The dipole moment is a measure of the polarity. So not the electronegativity, but the polarity. So you can actually measure the polarity of an entire molecule, not just one bond, by looking at this quantity called the dipole moment. And so that's up in this graph here. You can see that, I think. Yeah, so you've got, for each of these, there's this set of structures and they're given a name. That name corresponds to something called a functional group, but all you need to know is it's a category or a type of molecule. So you're given 5 different ones, or I'm sorry, 4 on this page, and then there's one later. Then you're given the structure in a condensed structure format, like we talked about last week. Then the molar mass, that's an indication of how big the molecule is, so the size of it has to do with the atomic weights that we talked about a couple weeks ago. If you kind of add all the atomic masses up for the whole molecule, you get the molar, what's called the molar mass. Then you've got this dipole, this measure of polarity. You've got the boiling point, which is the point at which a liquid can become a gas. So the temperature at which the liquid of that particular molecule becomes a gas. And then the water solubility. How many grams of this go into 100 milliliters of water? So if you have 100 milliliters of water, how much of these compounds can you put in before they separate out and form a heterogeneous mixture? So you can see there's a big variation there. So like these alkanes up here have very low water solubility, grams per 100 milliliters. So that means if you have 100 milliliters of water, you can only dissolve, less than 10 milligrams, which is a tiny, tiny amount of these things before they precipitate out. On the other hand, if we look at this category of molecules, the smaller ones here actually have, well, hold on, let me move that up so you can see. The smaller ones have infinite solubility, which means you can add as much as you want, and eventually you'll have actually more of these things than the water, but they'll still be miscible. They'll still be mixable without forming a heterogeneous mixture. And then as you go down this column, you see that the water solubility starts to drop off. And some of the questions later on are going to address that, and you're going to have to think about why that's happening. So that kind of explains this table and what the different columns are. So then you want, just like before, we want to use that information to go through the questions here. So looking at these dipole moments, which functional group is most nonpolar? So we would look at the various dipoles in the various, in the various categories, and the most nonpolar is going to be the one with the smallest dipole. These dashes here, I believe, mean that that's not known or something like that. But the smallest one here are these with the 0 dipole moment. So I will, the functional group that's most nonpolar is alkanes. Daisy asks, this won't be on the test, correct? Yeah, you're in the wrong class again, Daisy. This is the other one. This is Chem 103. So it will be on their quizzes, but not on yours. But actually, the polarity and stuff will be on the Chem 100 test also, but not in this context. We haven't talked about organic molecules yet. It says Chem 100. Oh no. Oh yeah, you're right. It does. Hold on, let me change it. I'm sorry. Thank you for letting me know. Okay, I think I changed it. We'll see if it actually changes because we already started. Okay, totally not your fault then. Sorry. Okay, moving on. So you've got the alkanes, which are the functional groups that are the most nonpolar. And then in general, do the polar compounds have higher or lower boiling points than nonpolar compounds? So we will look up at the table. And again, we can look at the ones that are nonpolar versus the ones that are polar and kind of make some general conclusions about boiling points. Now, because there's a big list and a big variation in numbers, we have to think about how to compare these things so that we're comparing similar molecules. And the way to do that is to look at the size. And I think it tells you that a little bit later on. But if we look at molecules of comparable size, like let's say an alkane that's about 44 grams per mole and an alcohol that's 46 grams per mole, that's about the same size. So now you see a massive difference in boiling point between those two, and that maybe has something to do with the polarity. So you can make some conclusions about that and answer that question. And then within the molecules themselves, we want to know how the boiling point changes as the molar mass increases. So again, you go back up to that table, and you should be able to see a pattern. Okay. So what this all ends up being about is attractive forces between compounds. So as the compounds have stronger attractive forces, that affects their boiling point, and also their water solubility in some cases. And then so much like the other packets like this, you're going through and making some conclusions and trying to figure out what is going on based on the data in the table. And then once you get down to here, you get a little bit more detailed information about what's really going on, and some of those other readings that I linked on Blackboard will help you with that as well. So just to explain a couple more questions that are often confusing when we've done this in the past in person. This question number 10, suppose that we consider anything over about 1 gram per 100 milliliters to be soluble. Then, considering the water solubilities of the alcohols, ethers, and amines in table 1, the presence of one polar functional group is sufficient to dissolve a molecule containing about how many nonpolar carbons? So let's look at what that means. Go back up to our, I don't know why this is being so slow right now. Up to here. So if we look at, for instance, alcohols, so this OH is is the polar functional group. That's the part of the molecule that is polar because, as we talked about earlier, the OH bond is the polar bond there, and the CH stuff is nonpolar. So you've got this kind of polar piece and nonpolar piece. So that question is saying, how many carbons can you have on the molecule with one polar functional group before you lose that solubility? So the way you see that is you can look over here at the water solubility, and you can see that you start with infinite solubility, and then it sort of drops off. And then like right here, you can see it crosses between, it crosses that 1 gram per 100 milliliters. So under here is where we say that's starting to be not soluble anymore. That is no longer soluble. So that we can also look at that for the other types of functional groups as well. So for example, if we look at the amines, we see similar behavior. The shorter chains with the few carbons are infinitely soluble, and then somewhere right around here, it goes around 1 gram, which we're saying is no longer soluble when it drops. So that question is saying for each of these different kinds of functional groups, how many carbons can you get before you drop below that 1 gram per 100 milliliter threshold? All right. And then for the next one, these pictures of hydrogen bonding, the key to that one is the description up here. All right. So this is describing hydrogen bonding, and you need to read that really carefully, and that will give you the clue to the answer for how you should actually draw that. All right. And then one of the main keys to this whole thing, or not keys, I'm sorry, goals of the whole thing, is question number 5. So I'm going to star that. This is the kind of thing that you'll end up seeing on the next quiz that I want you to really be able to do. Can you look, the whole point of this whole activity and thinking about polarity and structure and all of that, the whole idea there is, can you actually look at a structure and from just the chemical structure itself, can you make some conclusions or some guesses about its physical properties. So about boiling points, about water solubility. So this one and this one are some little like tests on that. Can you just look at a structure or a set of structures and figure out what's going to have a higher or lower boiling point? And if you can't, or you're just guessing, then go back to some of those activities up here and really think about it so that you can justify it to yourself. When we do some quizzes and stuff about this, I'll ask you to do something similar to this, and then I'll ask you to explain your answer just like here. So it's not about kind of guessing, it's about thinking about the rules or the patterns that you see in this activity and using those to make conclusions about some new molecules. All right, and then as usual, just like with the other ones, don't worry about that. Okay. So that's this week. Additionally, there will be a quiz that should come out sometime. I think it comes available today. There is lab on Wednesday for half of you. The other half should be working on your at-home proposal number 2, and then the other stuff that we generally do throughout the weeks, the article report, and this will be our new content. So if you have any questions, please reach out to me on Discord or email, and let me know how everything's going. Please get this started as soon as you can. There's just too much here to try to finish it all on Sunday. So yeah, please get to work on this as well as the structures from last week if you haven't already. And I'll see some of you on Wednesday. Otherwise, talk to you online soon. Bye.